Let's look at a special case of a horizontal circle called a banked curve. Most streets are flat, but sometimes the street is angled one way or the other, which we call a banked curve. It's embanked, and we're going to be looking at why that would happen. So here's an extreme picture of a banked curve. I'm not really sure why there's a bus on the banked curve, but there is. Sometimes you might see this on the curved portion of the stadium at like NASCAR or something like that, where the cars are going around a circle and the surface itself is tilted up. So we're going to draw a cross-sectional view. If we look at the picture on the right, you imagine sort of a cross-sectional cut through this. Can you see it's going to form something like a triangle, right, where the surface would be like the hypotenuse of the triangle. So let's draw that here, where we're looking at the car coming directly towards us. Now, you don't have to get real detail with your picture of the car. You can draw a box for all I care, but the angle theta is the angle of embankment, the angle that the surface is tilted at. And what we're going to do is we're going to develop an equation, a way to figure out how fast the car can move around so that friction is not even necessary to keep it from sliding up or down the embankment. Now, we have to keep in mind that the car is moving in a giant horizontal circle, because when you first see this picture, your natural inclination is to say, this looks like an inclined plane. But it's not, right? For an inclined plane, the object is constrained to move up or down the incline, but that's not what's happening. Look at the picture of the car. It's coming directly towards us, right? So the car is going around this giant horizontal circle. We're looking at it from the side. So this is definitely not an inclined plane problem. Okay, so we're going to draw a free body diagram, so why don't you go ahead and first draw some information off to the side, acceleration and net force. I wouldn't draw the velocity because right now the car is coming directly towards us, and that's going to be very, very difficult, so don't bother with that, but do go ahead and draw the acceleration and net force for this object. All right, so remember, it's going in a giant circle. We know circular motion is accelerated motion, and acceleration always points towards the center. So hopefully you drew this, right? The center of the circle is over there to the right. So if the triple acceleration points to the right, the net force points to the right. And so here we see, again, a big difference between this and an inclined plane problem. In an inclined plane, the object accelerates down the incline. The net force points down the incline, right? But that's not this situation. This is definitely not an inclined plane problem. Okay, so go ahead and draw the free body diagram. Pause the video as you do. All right, so remember, the whole point of this is to see what speed you can go at so that friction is not even necessary. So of course we have weight pointing straight down, and we've got a normal force pointing perpendicular to the surface, in this case up and to the right, and there's no friction, so there's the entire free body diagram. And so you're saying to yourself, hey, this looks an awful lot like an inclined plane problem. But remember, it's not an inclined plane problem. Why? Because remember, it's not accelerating down the incline, it's accelerating inwards towards the center of the circle. Okay, so what do we do next? Well, we want to do some sigma F equals ma, which means we have to resolve some forces into components. So why don't you just pause the video and think through what you want to resolve into components. And again, your natural inclination is probably to resolve the force of gravity into components because that's what we did for an inclined plane. But let's review, why did we do that? What was our strategy? The reason we resolved the force of gravity into components for an inclined plane problem was that the force of gravity somewhat contributed to sigma F, because remember, sigma F pointed down the incline, and normal force, being perpendicular to the incline, couldn't do anything. But that's not this problem, right? Here, sigma F points inwards to the right, and the force of gravity points straight down. There is no way the force of gravity could possibly contribute to sigma F. So what are we resolving the components? Yeah, it's normal force, right? Again, this is not an inclined plane problem. This is something completely different. So go ahead and draw the components for normal force. Okay, so it's going to point like this. One component pointing inwards, one component pointing upwards. Then, of course, we scribble out the original normal force. Now, normally, of course, we really should draw this on a separate free body diagram, but just because of the space on my screen here, I'm not doing it. But, if you want to draw a separate free body diagram, good for you. Okay, so now we get to play our favorite game. That's right, find theta. All right, let's see if we can get theta into the triangle. So pause the video, see if you can do it on your own. I'll give you a little bit of a hint. Let's draw a horizontal line here. All right, so you have a horizontal line here. Hopefully you see some alternate interior angles. There's the z, so theta is going to be up here. That's good. And then normal force is perpendicular to the incline, so what's this angle here? Yeah, this is theta. This is not theta. So what's this angle up here? That's theta. There we go. Gold star. Stickers for everyone. We got theta into the triangle. All right, so go ahead and figure out which component is which in terms of resolving normal force into components. You should see the vertically pointing force is adjacent to theta, so it's going to be n cosine theta, and the side over here, the horizontal component, is opposite, so that's going to be n sine theta. Okay, so now we're ready to do some sigma F equals ma. All right, so it's going in a circle horizontally, so we do sigma F equals mac, right, for centripetal acceleration. and we look to see what's pointing towards the center, and we see it's only n sine theta, right? So, positive n sine theta equals mv squared over r, right? Because we want to get the speed into this. The whole point is to find the speed, so friction is not necessary, so replace a sub c with v squared over r. Let's see if we can simplify this even further, right? Let's see if we can get normal force out of here. So let's now look at the vertical dimension, right? And vertically, as the object is going around in a horizontal circle, what's its vertical acceleration? Well, hopefully nothing, right? If it's going in a horizontal circle, its vertical acceleration equals 0. So what's going to happen here? Well, what's supporting mg? There's only one thing pointing up. It's going to be n cosine theta. So n cosine theta equals mg, which again is very much different from an inclined plane problem, right? An inclined plane problem, n equals mg cosine theta. Here, n equals mg over cosine theta. Definitely not the same thing. Okay, so I want you to go ahead and combine equations, get this into here to get rid of normal force, and see if you can solve for an equation for speed. All right, so we drop mg over cosine theta in here for n. And then we should be able to see mass on both sides. It's going to cancel out, so this is going to be independent of mass, as happens so often. And we have sine over cosine, and we should all recognize that, of course, as tangent. Good. All right, so now let's go ahead and solve, and we should be getting the square root of rg tangent of theta. Is this a new equation? Well, I'm not really going to box it in because it's really only for one situation, right? This gives one single speed so that friction is not necessary, so this object can move around on a banked curve and not slide up or down. So why is the surface banked? Well, the whole point is that we should be able to traverse this at this speed without friction. If we go faster or slower, we'll need friction up or down the incline. But let's say it's a very slippery road. Maybe it's in winter and it's icy, right? And so if there's going to be ice there, there's not going to be enough friction to help us out. But look what happens. We don't even need friction. N sine theta pushes us towards the center, causing the centripetal acceleration. And this way, we remove the need for friction. Whereas on a flat curve, friction was necessary to make sure the object accelerated towards the center. So what happens if the car is not moving at this speed? Well, let's consider, right? Let's say if it's moving too fast. So if you've ever seen NASCAR and the cars move around too fast around the curve, which way do they tend to go? Yeah, they tend to go sort of up away from the center, and they might crash into the wall at the top. And so that means it's going to try to go this way up the incline, right? Let's consider what's happening. We're not changing g, we're not changing theta, but r can change. And so if it's going at a speed faster than this, well, it's going to try to go to a position, a value of r that's larger, which means farther away from the center. And it can only move up the incline, so this makes sense. It's going to be going up the incline this way. But if there's enough friction there, it will hold it back, which means you need a friction force down the incline to prevent that from happening. What if the car is moving at a speed slower than square root of rg tangent of theta? Well, that's when you see in NASCAR, the cars slow down and they go inwards towards the pit, maybe for some sort of repair or something like that, right? And this makes sense because if we're not changing g or theta, and it goes to a speed slower than this, it's going to try to go to a radius that's smaller, right? In this case, down the incline, closer to the center. In which case, if it doesn't want to do that, we need a friction force up the incline, preventing it from sliding. So again, this is the one speed, what we call a critical speed. If it's moving at this one speed and only this one speed, we won't need friction either way, up the incline or down the incline, to make sure it goes around the circle.